Hello students, let us go to understand about isomerism because there are so many questions related to that isomerism, especially stereoisomers, optical isomers, geometrical isomers, cis and trans isomers. There are so many questions. So let us go and understand the complete idea about that isomerism. So today our topic it is isomers only. Okay, so what do you mean by isomers? Isomers is nothing, same molecular formula, but it differs in physical and chemical properties. Okay, now isomers, there are two kinds of nature. One it is structural isomers, the other one it is stereo isomers. What do you mean by structural isomers? So the same way here, same molecular formula but different structural formula, different connectivity, different position, different functional group. In that same molecular formula only, there will be different categories will be there. So that is what structural isomerism. Stereoisomerism means here same molecular formula, same structural formula also, but spatial arrangement of atoms or groups will be vary. So that is called stereoisomers. There are many questions related to that stereoisomerism, especially about optical isomerism, enantiomers, chiral, and a number of questions, cis and trans questions, and all comes from this categories only. So let us go and analyze this. What is this? And we'll go some more questions related to this topic. Okay, there are more than 500 questions related to this topic. In that, some we are going to see to that. Okay, now let us go for it. Okay, now here structural isomerism, stereoisomerism, just now I mentioned. Okay, what are the types of structural isomers? In that, chain isomerism, position isomerism, ring isomerism, functional isomerism, metamerism, and tautomerism. Metamerism and Tautomerism. So these are the types of structural isomerism. Whereas stereoisomerism, there are two categories are there, for configurational and conformational. Conformational at present it is not required for us. Okay, now configurational isomers, that is divided into two groups. It is geometrical isomers, optical isomers. Now optical isomers only, there are so many questions related to that topic. Even here also there are so many questions. Let us go and analyze what is the complete idea about this topic. Yes, let us go for it. Now let us go and analyze each and everything with the examples. So examples are really will give the better idea about this topic. Okay, now chain isomer. What do you mean by chain isomer? Isomers having different length of main chain. Okay, now for example, C4H10. C4H10 generally we can say N-butane. Okay, so N-butane bond line structure we can go 1, 2, 3, 4. Okay, so this is N-butane we can say. Or else one more way we can identify. This is isobutane or else 2-methyl propane. Okay, now the other one C5H12. If we go in that means, okay, 1, 2, 3, 4, 5. N pentane. Okay, in another way, 2-methyl butane or isopentane. Okay, now next one more thing also. This also, see, everywhere C5H10 is there, sorry, C5H12 is there. No, in that way you can identify 1, 2, 3, 4, 5. In each thing there is a molecular formula according to that. So same molecular formula but different structural formula. The what it is, the length of that position will be vary. Okay, now this is N butane, this is N-butane. These and all you have learnt in grade 11, but still there are some questions related to this topic. 100% you have to be thorough. Okay, now this is what it is. Isobutane also you can write it. Isobutane or 2-methyl propane. Okay, now this is N-pentane. N-pentane. Then this is isopentane also you can write it, or else 2-methyl butane. Okay, so isopentane. See, generally, second point which is attached, we can say iso. Now, the third one here, neopentane, also you can say 2,2-dimethyl propane. In this way, also you can say. Okay, now here you can put it neopentane. Okay, neopentane, it's a common name, but 2,2-dimethyl propane. Right? So that is the way you can identify. I hope you're clear with this chain isomer. Suppose if they are giving any formula related to this point, are you able to identify? Oh, okay, now for example, test yourself question I would like to give you. Okay, now C6H14. Okay, how many isomers are possible? Can you guess how many isomers are possible? Okay, if you are thorough means you are able to identify how many isomers are possible. In that way also they will ask. Hope you're clear with this chain isomer. The second one, position isomer, we are going to see to that. Now the next one, position isomer, what it says, isomers having different position of the functional group. Okay, let us go and identify that with the example. Okay, position isomer, example CH3, CH2, CH2, Cl. Okay, now the same way CH3, CH, Cl, CH3. Same molecular formula but differ in the position. Okay, now I will give one more example. Here, double bond attached over here. Now the double bond attached in the middle. Okay, now the same way here. Cl, here Cl. The same way. Cl and Cl. Okay, the other one. Cl and Cl. Okay, now what are the difference between this? Okay, now here. Now you see here, one chloropropane, two chloropropane. Same molecular formula, but the position, the substituent group attached in a different places. So that is differs in that. Okay, now this is one butene, one, two, three, four, one butene. This is two butene. Same molecular formula, but differ in that position. Now here, one, two, three. That means 1 and 3 dichloropentane. Here 2 dichloropropane. 1 and 4 dichloropentane. So in that way we can identify very easily the position where it has attached. So in that way they will identify. They will give the questions how to go for the position isomer. The position will be vary. Okay. Hope you're clear with that position isomer. Okay, you are not supposed to confuse with that position isomer and functional isomer. Functional isomer will be vary. Position, that same position only will be vary. See, here in that first position, here in that second position, here in that first position, here in that second position. The same way here also, position will be vary, but not functional group will be vary. But functional group, when we are coming to that next one, functional group only will be vary. Now, for example, here alcohol, ether. Okay, I'll give that. Hope you're clear with this isomers of the position of the functional group. The second one, hope you're clear with this position of the functional group. As we are going for that, what it is, functional group, you will come to know where it has, how it has changed. Hope you're clear with this positional isomer. The position will be changed, but the same functional group only. Position only will be changed. Hope you're clear. Now, the next one, functional isomers I have taken. Okay, ring isomer, after that we can see. Because functional isomer, why I have taken? No, because that positional isomer which is interrelated. The functional group which is vary in the position. But functional isomer, functional group only will be changed. Okay, let us go for the. Okay, now isomers having different functional group as I mentioned. Okay, now the first one, through example we can identify very clearly. Now the first one here, CH3, CH2, OH. Okay, the same way here, CH3, OCH3. Okay, now CH3, CH2, OH. Now, how many carbons are there? Two carbons. How many hydrogens are there? 5 plus 1, 6. The same way, 6 and 2. Here, now you see, let us write some more examples we can identify. Okay, now the next one, CH3, CH2, C double bond O, H. Whereas here, CH3, C double bond O, CH3. Aldehyde and ketone. Third one, CH3, CH2, C double bond O, OH. The same way here, another one, CH3, C double bond O, CH3, CH3. Okay, now see, now this is actually acid and acetate, that is ester. Now fourth one, R. General formula R, NO2, nitroalkane, R, O, N double bond O, alkyl nitrite. Okay, now the next one, fifth one, R, C triple bond N. The same way here, R, C, N triple bond C. Cyanide, isocyanide. The same way, sixth one, R, SCN, thiocyanide. The same way, R, CNS, isothiocyanide. Okay, now these are all the examples for the functional isomer. Okay, now let us go and identify. Here, as I mentioned, alcohol, this is ether, completely vary. Now, functional group which is not attached to anywhere, the functional group only will be vary. Okay, now here, this is alcohol, this is ether. Now, this is what it is, aldehyde, this is ketone. Both are same molecular formula, but differ in the functional group. Okay, now this is acid, COOH. This is ester, COOCH3. Okay, now this is nitroalkane, alkyl nitrite, and this is cyanide, what it is, alkyl cyanide. This is isocyanide. This is same way, thiocyanide, isothiocyanide. Okay, I'll give one more example. Hope you're clear with this. That is differ in the functional group. Even amino group also, I would like to give one more example. Here, CH3, CH2, CH2, NH2. This is primary amine, and this is CH3. This is primary amine. Now secondary amine also I can mention. CH3, CH2, NH, CH3. This is secondary amine, and here tertiary amine. CH3, N, CH3, and here CH3. So this is the tertiary amine. So these are all the examples of what it is, functional group. Hope you're clear that idea about what is that functional isomer and positional isomer. Difference between functional isomer and positional isomer. Hope you got that complete idea about that positional isomer and functional isomer. Clear? Okay, if you want, you can take that screenshot also. I hope you know the names also, because that name, it's a mandatory. I hope you know the name. See, CH3, CH2, COOH, acid group. Whereas here, ester group, and this is nitroalkane, alkyl nitrite, and this is cyanide, alkyl cyanide, this is isocyanide, and this is thiocyanide, this is isothiocyanide, and this is primary amine, secondary amine, tertiary amine. The next topic, it is that only, nitro compounds. Okay, hope you're clear with this. Okay, let us go for that ring isomer. The next one, ring isomer. A ring isomer, it's very easy. Functional group of isomers having open chain and cyclic chain. Okay, same molecular formula, different structural formula. That only we are going through all these things. Okay, now here I would like to give one small information. Cycloalkane and alkene general formula are same. You know, CnH2n, that is general formula for alkene. The same way, cycloalkane also CnH2n. Okay, so naturally it comes under what it is? Isomer. Okay, as we are seeing that examples, we will come to know the first one. CH3, CH double bond CH2. Whereas here, second one, CH2 double bond CH, CH2OH, allyl alcohol. Here, third one, CH2 double bond CH, CH2 NH2. Whereas here, NH2. Okay, now can you give the name for this? This is propene, cyclopropane, you know very well. This is allyl alcohol I just mentioned. Can you give the name? I'm asking that IUPAC name. Okay, prop 2 ene 1 all, OL. Okay, now this is cyclopropanone. What do we call? Cyclopropanone. ONE. Okay, because double bond O. And now next one here. The same way, one amino. One amino. Prop 2 ene. One amino. Prop 2 ene. Then the same way here. Cyclopropanamine. Cyclopropanamine. AMINE. Okay, so these are the way we can identify. Hope you're clear with this. Easily we can identify. So this is the way we can identify for that what it is, ring isomer. Now metamers and tautomers, there are so many examples and because there are so many questions related to that topic. Okay, let us go for that. Now the next one, metamerism. Isomers having unequal distribution of alkyl substituents around the polyvalent functional group. So here we are just to correlate that positional isomer, but both are different, only slight difference, but not same. Okay, now here positional isomer means what it is, that the functional group, the position has changed. Okay, alkyl groups will be same, position of the functional group will be changed. That is called positional isomer. Here, functional group is fixed. Only thing, alkyl groups will be vary. That is that to what it is, unequal distribution of alkyl substituents. Okay. Now let us go for that example. So you will come to know the first one: CH3, CH2, O, CH2, CH3. Same molecular formula, different structural formula in that way. Here CH3, O, CH2, CH2, CH3. Okay, now third one, CH3, O, CH, CH3, here CH3. So that what it is? There is a slight minor difference. The position of that what it is, that functional group as fixed. Only thing what it is, alkyl groups vary, unequal distribution. The same way, one more example also I can give you. Here CH3, CH2, C double bond O, O, C, CH3. Okay, this is one. And one more thing, here CH3, C double bond O, O, C2H5. Okay, in that way also we can identify both. In metamers, one more example I would like to bring it here. CH3, CH2, N, CH3, CH2, CH3. Okay. Now that different kind we can bring it. CH3, N, CH3, CH2, CH2, CH3. Then third one, different position, no, CH3, CH, here CH3, N, CH3, here CH3. That means now you have to check whether how many carbons are available. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. See, unequal distribution. See, commonly what it is, functional groups. Functional groups are fixed. Okay, functional groups are fixed. Only thing, unequal distribution of alkyl substituents are very, what it is, a fixed position of that functional group. Only thing, carbon group, it is vary. So we can identify very easily that metamers. Okay, now we are going to see the tautomers, which is very important. Okay, as we are looking at that example only, we will come to know that idea, then we can solve the problems related to the question. Okay, most awaiting part, tautomerism. It's a functional group which arises due to transfer of hydrogen atom or proton from one atom to another. Structures formed by tautomerism, it's a dynamic equilibrium. Yes, as I'm giving that example, you will come to know very clearly. Okay, now for example, H, C, triple bond N, at reversible. Here C, triple bond N, H. So the hydrogen atom shifted the same way. O, H. Here C, triple bond N. The same way here also, reversible. See here O, double bond C, double bond N, and hydrogen. Actually, resonance takes place here also, shifted here, hydrogen atom or proton. Okay, naturally, this takes place in keto-enol tautomerism. As we are going through the keto-enol tautomerism, number of times they asked in the question, what is keto-enol tautomerism? Keto-enol tautomerism occurs in alpha hydrogen, that means in the carbonyl compound naturally. Keto enol, enol tautomerism. Okay, now here in this point, here keto-enol tautomerism occurs only in the carbonyl compound. That too, what it is, alpha hydrogen should be there. Okay, now in this way, carbon connected with the 3 hydrogen CH3, and here C, double bond O, here H. In this, which is that alpha carbon, which is that alpha hydrogen? Of course, this is the functional group, aldehyde, carbonyl group, which is attached with it. The next carbon, it is alpha carbon. The hydrogen which is attached, it is a alpha hydrogen. Now, what happened here? So here what happened? Transfer of proton, hydrogen atom transfers. So naturally here you will get CH2, double bond, one hydrogen gone over there. So CH2, C here OH, H. Okay. Now the same way, another one, keto group, another one more example I would like to give you here in this point. Pakka keto group. This is a keto group. Of course, this is a keto group. This is a aldehyde group, that is a carbonyl carbon. Okay, now CH3, CH3, C double bond O, CH3. Okay, now here this is a keto group. Okay, now here what happened? CH2, double bond C, OH, CH3. Okay, so this is keto and this is enol. Keto and this is enol. OL, enol tautomerism. So this also, this point only we have to consider. Keto group and this is enol group. Okay, one more example I would like to give you. Other example, cyclohexanone. Okay, double bond O. here hydrogen. Okay, alpha hydrogen. So what happened here? Here you will get enol form OH and here double bond. Okay, now here this is keto form and enol form. Enol, small e. Okay, now OL, just mention because AL, OL, it's very, very important. So please mention in that way. Okay, now here, generally we will ask one question. Keto form is more stable or enol form is more stable? Why? Because it's a reversible symbol, it is there. So definitely we will ask that question. Okay, now keto group is more stable than enol. Why? You know, it's a partial positive and partial negative character, it is there. See, this is a negative and this is partial positive character. So why? Because it's a partial ionic character, it is there, which is having partial ionic character. Keto group is having partial ionic character, so naturally which is more stable? Keto group is more stable. But sometimes enol form also it is more stable. Now let us go and identify where that enol form is more stable. Okay, now in that ketoenol tautomerisms may occur in both acidic medium as well as basic medium. Okay, now where that enol form it's more stronger, let us go and identify. But generally keto form is more stable. Why? Because it's a partial ionic character, it is available in keto form. Okay, now next one more thing here. Suppose this formula double bond O, here double bond O, here hydrogen, here hydrogen. Okay, now keto form. Now enol form, how it happens, you know, like this. Okay, now here enol form means one, here one O, here hydrogen. Okay, now here double bond will be there. Here as it is, it will be same only. Only one point it will be vary. Okay, now what happened here in this point? Here intramolecular hydrogen bond may occur. No, so intramolecular hydrogen bond means it is like aromatic character. So naturally enol form, enolic form, it is more stable, more stable. Okay, now one more example also I can give you. Here the same way only double bond O, here also double bond O, the same character. Here actually this point acetyl acetone I have taken. Now here also the same, here OH will be there, here double bond O and yeah, OH, I just put it in this way so that it forms like aromatic character. And here what it is? Double bond here, because here keto form and here this is a enol form, no? So what happened here? This point hydrogen bond formation, hydrogen bond. So hydrogen bond formation, naturally intermolecular hydrogen bonding, it will be more stronger, more stable in this point. Okay, one more example also I would like to give you here, like this double bond O. Okay, this is different equation. Okay, now the same way here hydrogen is there, so here actually naturally you will get phenol structure, aromatic structure. Okay, now here one OH. See now, here what it is, see double bond one, here adjacent double bond, but there is no double bond over here. But whereas here there is OH and you are getting what it is, phenol structure only. So this will be more stable. Enol form is more stable than keto form. Hope you're clear with this, all these points. Here, main point I would like to mention, it's a dynamic equilibrium. Now, for example, R, C double bond O, here C, here hydrogen CH3. So, where it happens, generally, alpha hydrogen point only it will occur. Ketoenol formation takes place in alpha hydrogen. If they don't have that alpha hydrogen, definitely ketoenol formation will not take place. Okay, now two lone pairs of electrons are there. So what happened here? R, C, here O, hydrogen formation takes place. Okay, two lone pairs of electron. And here double bond C, H2. one hydrogen, that alpha hydrogen takes over here due to that resonance. Okay, now in this, what are the bond forms, what are the bonds broken? Now bond formed. So what are the bond formed? Carbon and carbon bond forms here in this point, carbon and carbon bond forms, and OH bond forms. See here in this, the bond broken, no? So here OH bond. So these are the bonds formed. This is pi bond forms. Okay, what are the bonds broken? Bond broken. So bond broken, where are the bond broken? Here CO bond broken, here C double bond or CO bond broken, and carbon and hydrogen bond broken, carbon and hydrogen bond broken. So these are the way we can identify. Okay, now generally you have gone through so long what are the tautomerism, when it happens, where it happens, those points and all you have gone through. Some of the compounds which do not take part in that tautomerism. So such kind of formulas definitely we have to go through. Why? Because they don't have alpha hydrogen. So generally keto-enol tautomerism takes place only, generally tautomerism occurs only in alpha carbon only. Now for example, suppose like this formula it is there. Is it happen for the tautomerism? No, you cannot get the tautomerism because it does not have alpha hydrogen. The same way here also. One more example. Double bond O here, like this kind of point and all, you cannot get what it is, tautomerism at all. Okay, now here double bond O, like this if it is there means you cannot get any, this kind of formulas also you cannot get any tautomerism. Benzaldehyde also, benzaldehyde, simple way, benzaldehyde. Do you think and this formulas, tautomerism can occur? No, it does not. Why it does not occur? Because there is no alpha carbon. Hope you're clear with that. Okay, now formaldehyde, tautomerism may occur. Can you guess? Hope you're clear with this. Thanks for watching. In our next video, we are going to see stereoisomers, in that geometrical isomers and optical isomers. In that optical isomers, there are so many points to be noted. That points in our next session we are going to discuss. Thanks for watching.